So thank you for coming. I am Marcelo Kuperman from Bariloche in Argentina. I am working in the group of statistical and interdisciplinary physics there in Bariloche. And the idea today is just to propose an open question and to talk about the possibility of trying to frame within the same formalism the formation of patterns when patterns are related to time and when are related to space. And the idea is just to discuss the possibility of, as I mentioned before, see whether there is a connection or if there is a possibility of trace a connection. It is not clear enough. So I will start with the first two equations. One that is an ordinary differential equation that is well known, that the logistic one, and then the Fisher equation that is the logistic equation with diffusion. And just to open the discussion and to as an introduction for the rest of the talk, we have, suppose we have a quantity n, and we have this. This is known as the logistic equation. And this equation has two equilibria, n equals 0 and n equal 1. This one is unstable, and this one is stable. So in time, the behavior of this sort of system would be something like that. If this is 1, this is time, this is n, this is 1/2. If we start from here, in time, the evolution of this number n would be like this. If we start from here, it would be like this. And if we start from here, it would be like this. So the solutions, no matter from which is the initial condition, the solutions will go asymptotically to the only one steady equilibrium that is n equal to 1. This is well known. So this is for the logistic equation where there is no space. Now, suppose that we are including diffusion. So now we have something like that. Plus. So for this equation, we cannot find an analytic solution, but there is something that we know. There are two things that are interesting for this equation. The first one is if we are working in an open space without no boundary conditions, or if the space is infinite, so there is a possible solution that is something like that. There are fronts, traveling fronts, that move with constant velocity and with constant shape. They just travel, maintaining the shape and maintaining the velocity. And there is only one steady, there are many velocities, there are many solutions, but there is only one structural stable solution that corresponds to the Fisher velocity, that for this case is equal to 2. And the shape is something that can be somehow calculated. But the important thing is that the solution for this is a traveling front moving with constant velocity and constant shape. If on the contrary, what we do is just to consider a bounded space or a bounded domain. So what we can find is a solution with this shape. Suppose that I am asking Dirichlet boundary conditions. So I ask for the solution to be equal to 0 here and here at the border. So I have something like that. And if I start to shrink the domain, I will have something like this. And then something like this. So if I am plotting the maximum of the function, of the value, as a function of the size of the domain, what I will obtain is something like that. This is the size of the domain. This is the maximum. of the function, I will get something like that. So there is a sort of transition. There is a critical size for the domain. If the domain is not big enough, so there is no possibility for this solution to be different from zero. So this is something that is well known. But now what I'm wondering is what happens if we introduce non-locality? And by non-locality, I want to, what I'm meaning is non-locality in time means a delay equation, and non-locality in space is what we understand by non-locality space. So I will show you that there is something that connects both solutions or both behaviors. And the open question today is try to see, as I mentioned before, if there is a unifying frame for explaining those phenomena, or maybe to explaining those phenomena not from the point of view of a formal explanation, but at least from the point of view of a qualitative explanation. Okay? So let's move to the equation. So the first one is the equation, the logistic with delay. So instead of having this solution here where I have t and t and t, what I have is one possibility is to say that this term here will not be evaluated at the same time as this term here, but it will be evaluated in a different time. When I mean a different time, this can be evaluated throughout all the history of the previous times. So instead of just having a differential equation, I will have an integral differential equation. So I have this term Rn, and here instead of using n, what I am considering is all the values of n before the time t. So that's why I'm interacting from -infinity to t. But I can also consider a simplified version for that, and instead of considering all the times before t, just to consider one time before t, only one time delay. So that means that instead of having this u that is a kernel that has any shape I can imagine, this kernel is replaced by a delta function. So this integral turns into something like that. So this integral differential equation just turns into this delay equation that is, at least the shape is very simple. Okay, so we have the derivative of n with respect to time, and this is a logistic equation with a delay term in this part. Okay, this is one possibility for introducing the delay. This is the one I'm trying to show you today. So it is well known that there is no analytic solution, but numerically we can solve this solution, and we will find that depending on the value of t, or depending on the value, the relationship between t and k and r, there are three different behaviors. There is the usual behavior. The solution in time will behave the same way it behaves when we are not considering a time delay here. Then there is a second kind of solution that is something like that, that is oscillatory but with damped oscillations. And then there is another solution that is a solution when there are sustained oscillations with non-changing amplitude and with a very clear period of frequency. Okay, so we have three different solutions. And
the period, I think, is T, no? The period is capital T.
Yes. No. That depends. Well, that depends on the relationship between R and T. So according to, yes. So these are the three regimes, and depending on the value of R times T, we can find the monotonic solution, the damped oscillations, or the limit cycle, that is something with the behavior when there is oscillation. And
those parameters, they seem very similar to the one where you have a linear version.
Yes.
That's because you somehow find those parameters. What is it that you do?
What do you do to find these parameters? Okay. Okay. You do what you have to do is that to find this value for the parameter, what you have is to consider that Yeah, you have a linear, yes, you have a linear, yes. What you do is a linear stability analysis for the solution, and you consider that there is a perturbation, and then you make all the analysis, and what you can realize is that
Characteristic equation is transcendental.
yes, this is the characteristic equation that is transcendental, and if you consider that this lambda can be complex, if the lambda is real, the only possibility for lambda being real, if you follow these calculations, is that lambda should be negative. Okay, so this is the solution when there is no oscillations and the steady state is stable. Okay, and this corresponds to this solution here. Yeah. But then there is also possibility of lambda being complex. And depending on the real value of lambda, you can get damped oscillations or you can get a limit cycle.
So you lost, I mean, on the linear one, you lost the divergent case. No?
Yes. But also, what you can do is just to try to figure out what is happening. And this is the equation, okay? And for this equation, when n is equal to 1, if n is equal to 1, the derivative will be equal to 0, okay? Because if n is equal to 1, this is equal to 0, so the derivative is equal to 0. So suppose that you are coming from here. You are coming, not 1 over k in this case, because k is not equal to 1. So k, sorry. When n is equal to k, this is 1, and so this is equal to 0. So suppose you are coming from here. You are coming from below k, and once you are here, n is equal to k. But n minus t is not equal to k, it's less than k. So this term is still less than 1, so the whole derivative is positive. So this goes on growing until at a given time you reach a time t when n at time minus t was equal to k. So at this moment the derivative is equal to 0. And from if we go on moving, so n time minus t will be greater than k. So at that moment the derivative starts to be less than 0, so that this starts to move down. And again, when you arrive here, the derivative is should be equal to 0, but n is equal to k, but n of t minus t is greater than k, so the derivative is still negative, so this goes on going down until you reach this value, and this value corresponds to a situation when n t minus t is equal to k, so the derivative is 0, and start to grow away. So this is more or less the origin of the oscillation. This is not something that explains that the oscillations will be stable and you will have a limit cycle, but this is something that can show you that the possibility of oscillation is there, and it's more or less simple to understand the origin. Yes, yes. In this case, yes, yes. So this is something that can tell you why there is a possibility of having oscillation. And this is clear, for time it is clear. But let's go to the situation when instead of having an ordinary differential equation, we have a derivative also in space. So we have a partial differential equation. And for that, what we have is something like that. Suppose that, remember that what I am referring as no local in this case is not something in time, but something in space. So the Fisher equation is the one I'm here. So I have here. So we have the diffusion term, and then I have here a logistic term. But instead of considering that this n is at the same point as this value of n, what I am considering is that this value of n is not only at the same point or at the same site where n is, but it's something that I should take into account a sort of non-local interaction. So if I am taking into account a local interaction, this term, instead of being just the value of n, is an integral over all the space of different values of n with a given kernel. I have to choose this kernel just to, depending on what I'm trying to model. For example, if I am trying to model the interaction between different species, this kernel can be a Gaussian, and meaning that the interaction with near individuals is stronger than the interaction with individuals that are far away from where I am at a given moment. Okay. So it is known, and I will use the blackboard again. It is known that for this sort of equations, if the kernel, now I'm talking about the kernel, U is the kernel here.
No,
F, sorry. F is the kernel here, and this is space. If the kernel is like a Gaussian, for example, with a long tail, there is no possibility of pattern formation. But if the kernel is bounded, for example, I may have a Gaussian that is bounded artificially, so it's not a Gaussian, but it's a Gaussian without the tails. So for example, this is something like this, a square function. So if this kernel is bounded, it is possible to find also spatial patterns for this equation, steady spatial patterns. So when you see the solution for that should be, as we have diffusion here, the solution should be something that is uniform. But when you introduce this kernel or this integral term here, and the kernel is bounded, there is the possibility of having oscillations in space, and steady oscillation, or patterns in space, not oscillation. There is a possibility of having steady patterns in space. So this is also a known result. So now the question I wanted to discuss and the proposal. So suppose that instead of having a kernel like this one, I have again a delta in the sense of the delta that I had when I considered the time equation, the time delay equation. So instead of this kernel, I only use a delta. So the equation is non-local, but in the same spirit of the delay equation, I am only evaluating the value of u at the same position of u here, but also at two different positions, one to the right and one to the left. And the idea is to evaluate one to the right and one to the left is because here I'm considering a second derivative and not only a first derivative, so just to preserve the symmetry. So what happens when we are considering this? We can obtain again patterns. So it's only as simple as only considering this very simple non-locality to get patterns. So, and well, this is what I wanted just to present and just to open this. Yes. Something like, yes, something like that, yes. So, okay, so.
That's, yeah, that's bigger.
Yes, but.
Yes.
Yes, here.
So it's, I mean, it's
Okay, but yeah, it's a bit more difficult.
Yeah.
But in a first rough
Yes.
feeling, it is something that.
Okay, this is the sort of idea I wanted to discuss today. Well, what is the connection between this? Let's talk about patterns in a general way. A pattern could be just a time oscillation or a spatial pattern. And just by considering very simple non-local terms, it is possible to get patterns. So the question is, it is possible just to get a very intuitive or easy explanation of what is happening. It is possible to frame this and the other equation into only a unifying frame. So that's what I wanted to present today.
One comment I have is that this study is getting of time.
Yes, but yes. Yes, you make you make this equal to 0, but then if you want to analyze the stability of the pattern, you need the time.
Yeah,
that's an important point. But yes, you can somehow analyze the possibility of pattern formation, saying that this is equal to 0, and you have the same. You have only an ordinary differential equation. Here I have diffusion, but what instead diffusion I start to use a different thing, like for example chemotaxis.
What happens with the stability? It's always stable or
well, there are strange things. If this is symmetric, and depending on the distance between, depending on the value of b, you can get depending on the value of alpha and beta. Here alpha and beta are not necessarily equal. If they are equal, depending on the values of alpha and beta, you can get patterns or there are no patterns. But if alpha and beta are different, you can get patterns that are traveling. They preserve the shape, but they travel. So they are not stable in the sense that the velocity is equal to 0, but the shape is steady. So you have traveling waves in the same way that you have with the other.
But not single front like in Fisher.
No, you have oscillations that just travel in time.
As a reciprocal interaction, it's not symmetric, I think.
Yes. It is known. Okay, that's this I didn't know.
You have enough freedom for the people. But here it's a bit difficult maybe to say such a thing because we have studied for a field with two components, like A and B particles.
Yes.
You have a scalar thing. You have a scalar field in mind. The scalar field, then I'm not so sure whether I can say this with confidence.
Okay, but we are just.
But for two components.
Well, let's.
So you introduce by this non-reciprocity, you introduce something like a chase between the predator and the prey. So
Yes.
that can cause oscillations, and then you have. So the difference is, of course, you have a spatial, you break the spatial symmetry, whereas I think of breaking, it's like somehow the interaction between species is asymmetric. Yeah, one is chasing the other one. Right. But if you break the spatial symmetry, I think together with the Laplace term, it looks as if it's a bit like this, right?
Yes.
So
yes.
you see that having an interaction with another point in space is like having another species that is
It looks a bit like this, right? As if there is a similarity between the two things. You break the spatial symmetry, you are doing something which is in spirit similar to.
So you are changing somehow the dimensionality of the system. Instead of having a one-dimensional, instead of having only one equation, it's like you have more equations that are hidden somehow.
Yeah.
Yeah, well, that's interesting.
Yeah.
So, well, this is what I wanted just to introduce and now and to promote the discussion. So
the corresponding case, I'm looking at the top, when you have kernel, not via delta.
yes.
So when you cut it off the Gaussian, that's when you get pattern.
Yeah, it is a cut Gaussian. Yes.
So the corresponding time of the delay that we have some u, whatever you have there.
Yes.
So what happens, when you have a delay, you can have this pattern, so steady pattern in time. So if you put something that, instead of speed and then it decays, instead of cutting it off, the delta is like a
Yes.
cut off. What happens? You lose those sort of steady patterns.
Yeah, if it is not bounded, you lose the patterns. And you can see that what you do to get the patterns is just to make a linear stability analysis, and then you Fourier transform the whole equation, and you can get the behavior of each of the modes. And for each of the modes, you can see whether the exponential is positive or negative. And
Yeah, that's now we have a pick up kernel. So go back.
yes, but let me show you. No, I have it not. No, I have not it here. I didn't put it. But if you suppose that you have this kernel, okay, so what you can do is just to Fourier transform the whole equation and proposing a solution that behaves like an exponential in time with a given. So the interesting thing is that as we have a Laplacian here, you can say that you can just use a basis for all the function u and using the sign, for example. You can use the sign as a basis for the sign function with different modes as a basis to be able to build up all these functions in, because they are eigenfunctions of the Laplacian. So you make a sort of you transform Fourier this equation, and as what you get is something that is written in terms of summatory of a sine or a cosine, depending on the boundary conditions. As the sine and the cosine are again a function of this operator, instead of having a differential equation, what you finish by having is an algebraic equation for the modes. And when you get that, you can just obtain the value of the exponential that is related to the time behavior. And if this exponential is positive or negative, will give you the stability or instability of the homogeneous state. And I'm saying that because if this kernel is not bounded, you will never be able to unstabilize the uniform state.
Yeah, but time has a cutoff t. No? So if you have the corresponding time, you don't have an integral over the whole space, so over the whole time. So if you have a cutoff, automatically you have a cutoff at time t. I mean, if you go back to the first.
You mean in time? You mean in time?
Yeah, that's what I meant.
Okay. Sorry. I didn't understand.
That,
yeah.
Yeah.
Okay.
So
Yes.
Your U, which is now your cutoff.
Yes.
Kernel. Now, yeah. So. Yeah. So what happens if you have a U which is not a derivative?
I don't know.
That's an integral, even if it's linearized. Then you have an integral. So what?
I don't know, because there was someone who presented something like that in the talks last week, and I don't know if it was she or he, but did the same thing. Instead of considering a kernel here, just move to a situation like that. Because it
Nice of which is the power law kernel reminds me of I think what's called a fractional integral.
yes.
So it goes in the direction of fractional derivatives. So you don't have a fractional derivative in front, but I mean, okay, we have to check the details, but it's something like that.
Yes.
Same idea that you have.
Yes, the same idea. Yes.
Marcelo, in the non-local version,
Yes.
spatial non-local,
Yes.
why did you put 3 deltas? Do you need 3? And you do
Just-
the same with 2?
But
Locality to 1.
if you have one, if you have only one, you have still patterns. The question is that as you have a second derivative, and you would try to maintain some symmetry in the derivative, so you put one.
No, but I mean 1.
You can use only one, like this, for example.
That's what I mean. You can do it.
Yes, but you when I cannot exactly remember what happened when. Yes, but he means to do beta equal to 0, for example.
He wants to omit the term, but
Yeah.
it's very similar.
Yes. Yeah. Again, there are situations when you can still get patterns, but the patterns will move in time. They will be the shape will be stable, but they will not be stable.
So to have them stable,
You need some.
the symmetry.
Yes, you need the symmetry. Yes. But anyway, there is a possibility of finding the condition just for this situation. There is an approximation that can be done, and you can analytically obtain when you will get no patterns and when you will get a pattern that will start to move. This is something that can be done analytically, not just again by Fourier transforming the whole equation and making some calculation. It is quite straightforward to.
That you can do it at the top.
Yes, yeah. This is quite straightforward to do, especially when you have here something like the delta. It is very easy to calculate. But again, you can do that. And my open question is it possible to understand this as only one phenomenon, not even if we have time in the first case and we have space? And maybe one of the answers is something is related to what you have been saying here.
So it's equivalent to having more.
Yes.
So could you say again the threshold for the B if you make alpha and beta unequal?
Yes.
But that's the threshold for B arbitrarily small does not suffice.
Yes. Let me see if I can find the. the manuscript I was working with. Okay. So this is the equation, and to perform the so what you can do is just to make a stability analysis just by Fourier transforming the whole equation, and then there is a possibility of finding a situation when you can just calculate the speed of the front. What you do is you transform Fourier the whole equation, and then you make some calculations proposing a traveling wave. So we are assuming that we have not a steady front, but we have a traveling front. And we propose that this traveling front behaves as a traveling wave or has a given velocity. So, and the important thing is that for these patterns that move, there is only one value of k. This one only mode that is present. So what we are assuming is that there is a mode that is moving, and only one mode. So we can calculate the speed for this mode, and we do that for this mode, just proposing a traveling wave, and we find this solution for these conditions that are the imaginary and real part of the Fourier transform, and this is giving us a condition for the velocity. So there is a possibility of calculating the velocity and knowing when the velocity is going to be different from zero. We can know when we will have a moving pattern or we will have a steady pattern. So this can be done. But this is not very clear. I was not planning to show you this, sorry for that. But it can be done. We can calculate the movement at which the velocity is starting to be different from zero.
This depends on.
Yes, depend on beta and alpha. Yes. Oh, yes. Yes.
Also,
yes.
This discrete terms with a finite amplitude, or is it only that?
Well, in this case, we are considering that A and B are equal to 1. Yes. Yes.
E is equal to 1 over 1. Will it still allow for a very small amplitude, or will it be completely gone?
This is something that.
There in Spanish.
Yes.
If we have another case, you have to check the calculation.
Yes. 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 We don't know yet. Yes.
It's even red.
In red.
Yes. Because this is work on progress. Yes. Yes.
So for the traveling wave, what you do in the usual Fisher case without any delay is composed of checking variables z equal x minus ct.
Yes.
So if you were to think about two variables, z1 and z2, one which is x plus a
Okay.
alpha and x minus same when you get an equation for the fronts.
But you mean two velocities, different velocities?
No, the same velocity. So the same front.
Yes.
Then have addition equation. That the difference between those x.
Ah, okay.
Is the
Yeah.
alpha minus beta or something.
We can try this. Yes. Yes.
Then the gradient is same for both.
Yes.
So
Yes, we can try it. It's possible. But well, the idea was not to get into the details of this calculation, but just to be more general and see what you think about the fact that we have the same phenomenon by considering different situations, and see whether, in your opinion, it is worth trying to understand them as only one single phenomenon.
So we have a missing ingredient, because the other one you just have the T minus capital T.
Yes,
And then what happens when you have a kernel?
yes, but this
So
is,
in a sense, like, to see some similarities, no?
yeah, well, I think that there is a paper by Chenise, Wolper, and Auger, when they consider also a general type of kernel. And yes, instead of considering this delta that we are just considering here, they consider a special type of kernel. The problem with that is that the calculations are not so straightforward. And also, we wanted to consider this deltiform type of kernel because the idea was just to compare the time delay with this spatial non-locality. That's why we wanted to get rid of the kernels, mainly because it is easier to have an intuition of what is happening.
Yeah, but my question still stands.
Yes, yes.
The kernel time is quite different because you have a cutoff of T, no? So formally, it's something.
I studied a problem with a kernel in time with a gamma function that could be solved. And you also have a Hopf bifurcation as a function of the shape of the kernel. But then, so you don't need a compact support of the kernel.
No.
But tails still have a oscillation.
Yeah, what we did here was just try to see, for example, if we have something that is deltiform, just to consider that alpha and beta can go very far from the points. It's like having a sort of kernel that is not bounded. But we found nothing interesting. We expected to find a sort of critical distance at which the pattern disappeared, but we couldn't find anything. No.
why would the pattern disappear?
Because for the time delay, if you are considering a kernel that is not bounded, the pattern disappears, the oscillations disappear.
Stay down. Fail. X. Beta, right?
In this case, yes, but we wanted to see whether we could obtain a sort of critical distance at which there were no more patterns. But at least with this, was not possible to find an equivalence between the necessity of having a bounded kernel for time and the necessity of having a bounded kernel for space. This also is something that could be analyzed.
Isn't it different time because you have a direction? If you start at 0, space.
Well, but in time also you have a sort of direction.
That should be
Yes. So formally they are not very different one from the other.
Marcelo,
Yes.
if you have the kernel in space,
Yes.
but not symmetric,
Yes.
so you shift it, so it's not centered in y equal to x.
Yes.
You also have the wave kernel.
I don't know. We didn't try this. maybe it is possible to, by following what these people did, maybe it is possible to anticipate whether there will be a traveling or non-traveling pattern. But we just wanted or what I wanted to show you, and this is what we did here, was just to consider the simplest situation. No, not speaking about, because if not, if we start to try to understand the shape of the kernel, maybe the simplest situation, that is the formation of patterns because the presence of a non-locality, a very simple non-locality, will be lost. So we wanted just to understand why a very simple non-locality as the time delay or just this deltiform kernel can induce patterns in time or in space. And try to see whether there is a possibility of just framing this situation as only one phenomenon. And see whether also if there is a sort of qualitative explanation. What you mentioned is something that is something that is giving me an idea of how to analyze this or how to try to make an interpretation of what is happening. Yes. 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 Yes.
But
it's still.
Like patient and delay in time.
Yes.
Where you make computation that are reached for a long range. There you go. It looks a bit as if you start to break.
Yes. Yes.
A similar way, normal delay. But the past shaping.
The future. Yes.
And not shape. That sense, it could be similar, or if you think of providing a prefactor that competes with a D, with a Laplacian.
Yes.
That sense, I think that there could be such a relation that would be quite expected to be.
Okay, well, thanks for the inspiration for that.
So I wonder, so suppose that now you have a non-local path, then you could also delay
Yes.
the non-linearity. So
Yeah.
can you destroy, no, suppose you are in the case where it's symmetric in space, can you destroy the given, but probably you need some delay with this of the given line.
Yes. Well,
I mean, it doesn't help.
Yeah.
But
no, but you have a lot of open questions that can just give us ideas of how to go on with this or what is worth looking for in this sort of situation. We wanted to start by the simplest scenario and then just to move to more complicated conditions.
We're checking out the literature on fractional generalization.
Okay.
I know that people have been doing that, but rather in terms of, I think, fractional derivatives rather than fractional integrals. So, if I understand correctly, yours is rather a kind of fractional integral, but people have been putting in fractional derivatives, but they did the same.
Yes.
Based on time. You are talking about the state about the traveling wave, so there may be a question.
Yeah, this is also a field to explore. Yes.
You know,
yes.
The states actually generalize the physical equation on these lines.
Well, that's nice. Well, yeah. Yeah, because one of the things that we face at the moment of studying that was where to look for bibliography, because there is not too much done, at least in understanding this equation as a delay or non-locality, but could be that we try to read the literature about fractional differential equations, we will find information. Yes. Okay. Okay, I will check that. Yeah. I remember the talk we had last week that it was about the fractional differential equations, and they just had something as the what I show with 3 regimes for the delay equation. Yeah. Well.
Any other comment?
Okay, no, thank you. Thank you for the ideas. Thank you for the suggestions, and there is a lot to check and to try to study, to go on and move with this. Okay, thank you.